All right, so my name is Thomas Hayes. I'm an assistant professor of practice in aerospace engineering at the University of Oklahoma. I have one of my students here, Jared Manning, to help me out for the discussion. And we do, would you mind?
Mark. Yep. March.
Yeah, pay attention.
Yeah, we do high power rocketry. We launch fairly large rockets for customers to
Okay.
You're good, Mark.
No, the video's fine, or the PowerPoint, either one.
Which one?
Let's go video.
Video.
Do your introduction, Walmart.
Most of you not really paying attention, not really paying attention. Because this is probably the most spectacular motor you're going to see this year. Oklahoma University performance. It's a 109-pound rock flying on the Cicero
That's the motor we shot.
5, 4, 3, 2, 1, hit it.
It's pretty fun. Thanks, Jared. So we get to do a lot of this with as many aerospace students as we can get involved. Thankfully, we do have some corporate sponsors that assist us in these launches, and we launch payloads for them. Because unfortunately, if you thought radio was expensive, try burning a $1,600 motor in 3 seconds. So this gives you this is fun because that's the size of a small telephone pole, and the flame is equal size. So as you'll see in some of our sensors and packages, and I'll try to get through this in the 30-minute window we have. Thank you. Is that some of the accelerations are rather extreme. The sensor goes up to 105 Gs, which is a bit much. But to describe what we have going on at the university, and something we're really trying to grow, is that we involve, I think one of these is a laser pointer.
Center one.
Oh, center, oh, that's not the right button. What'd I do? Oh, it's back, okay. Center one, we involve all of our levels of students. Mainly freshmen through junior, going to Boomer Rocket Team where we develop their skills. We get them going through level 1 and 2 and sometimes level 3 TRA, Triple E Rocket Association certifications. Level 1 starts with what, 2 to 3 foot rockets, relatively low impulse. Each one has an impulse designation. That means basically the thrust multiplied by the time it's provided. And basically, they just mean we certify them for increasingly dangerous rockets, increasingly sophisticated deployment electronics, increasingly sophisticated radio systems, etc. And do that in a safe way where the team can help train one another and develop. As they come out of this initial team program, we put them into a competition team senior year. Of course, sometimes undergrads get involved with that too, and we kind of welcome all to these groups as they're willing and able and have the desire. But we have an aerospace capstone competition team where actually we go to Argonia, Kansas to compete in the Argonia Cup. We went this last spring for the first time, got 3rd place, beat a bunch of other universities. All right, good job. And then collectively, we grab students that are really involved and have a lot of enthusiasm and surprisingly extra time somehow. And we employ them, have the opportunity to employ some of our best to go into rocket research at the undergraduate level. So at this point, we actually do fly customer payloads. We're actually mounting payloads in the top portion of the rocket, push the button, engineer the rockets to customer needs, And then once it lands, hopefully in one piece, we can let the customer download their data or collect the pieces depending on how the launch went. But it's really fun to go up there. And right now we have to go to Kansas. It's the closest place to launch with the airspace we need. They're cleared up to, if you need it, to 50,000 feet in a 7-mile radius cylinder. I think the standing window is only up to about 30,000. Actually, they're in conversation with the air traffic controllers you might expect throughout the launch event to get those higher clearances approved. A typical flight looks kind of like this. This is some of the data we get back from our onboard electronics, which you'll see much more about. They're contained in our avionics bays, which I brought a big example. That's the diameter of the large rocket we shoot. I brought a smaller example that might, it's all apart right now, but that's more indicative of some of our senior capstone, smaller size rockets. So it, of course, saves both barometric and GPS-based altitude, location, coordinate data. It saves speed, velocity, accelerations. We'll go over the sensors here in a bit. But just visually, that's the data plotted in Google Earth, and it's like, okay, it's a rocket flight, fine, until you realize each one of these squares is a half mile. That's a really high altitude flight. And this one, you'll notice also that the maximum speed, which call them 1,600 feet per second, that's Mach 1.57. So students are going supersonic, designing things with epoxy and fiberglass in the bays over here at Oklahoma University and breaking the speed of sound in Kansas. That's pretty fun. That's cool stuff as a student. This is some of what a chart might look like for the telemetry we get back. This is for a student flight. As you see, this is the one that actually is the highest speed we had in the past year. So not only is it supersonic, it's well into the supersonic range. And what's neat is you break the supersonic barrier in just a number of seconds. 3 to 5 seconds after you push the button, it's faster than the speed of sound on its way to, I think this one went 12,000 feet, something along that route. You have so many of these plots, they all kind of look the same after a while. But what's neat, see the boost phase, lots of acceleration, you're coasting most of the way up actually. I think this motor only burned for 2 or 3 seconds. You burn off the rest of your kinetic energy, trading it off. We have sensors, electronics that are constantly sensing change in pressure. Once they detect a peak, meaning that the pressure is no longer decreasing, it's starting to go back up. They also have tilt sensors that understand when the rocket is tilted over horizontally. And as the video showed, they're really, really good at popping the drogue chute up top. This particular rocket only had a drogue. It was light enough we could bring it down on one chute. So you see a fairly steady descent all the way back down to the bump at the bottom. But acceleration, orange, relatively smallish here on this rocket. It only hits, well, the scale's way far off. I won't try to guess at this moment, but acceleration is typically in the range of 5 to 15 Gs on some of the rockets. On the smaller rockets, the acceleration is actually higher because they're lighter. This is what our avionics system looks like. This is actually the 6-inch rocket diagram you see there on the left, but really, in terms of, right, yeah, they're identical. It's the same board, and our 8-inch rocket, that is actually nicely secured. But this is where we mount all of our electronics, radio systems. In fact, the antenna is right here routed, so this is just a little quarter-wave whip antenna to the main flight computer here. This is the system that records most of our telemetry. These two boards are dual redundant deployment devices. So not only do we have 2-stage deployment for recovery, we pop both a drogue parachute, a small one, and a large parachute. We have dual pyrotechnic charges, one primary and one backup that we usually program to detonate about a half a second after the fact, after the first one. So that way if one system runs out, a wire gets cut, battery, anything happens. It's electronics, they always work perfectly, right? Mm-hmm. We have the safety and redundancy of having something else ready to open the rocket up and put the parachute out. So what's neat is that these rockets are very large. This is where we started. This is one of our smallest rockets. So I think this launched at a 62-pound weight. The first launch didn't go supersonic. The second launch on this one hit 13,000 feet at Mach 1.3. So it's pretty fun to just push the button using someone else's money.
Why did the first one not go supersonic?
Different motor choice. So the first launch, we wanted to go easy on it and just give it a softer push without putting as much structural load, as much high velocity dynamic pressure onto it. The second launch, we put the higher thrust motor that was really going to take it into the supersonic range. But this is the radio side, the radio heart of our rocket system. That one board, this is the Telemega flight computer right here. And really this is the brainchild and the product of the company Altus Metro, owned by BDL Garvin. It's kind of fun going to these rocket events because As you might know from other radio events, you never really know who shows up. It's interesting to talk about their experiences, what they're involved with, and their capabilities. He's very big into open source, very big into AMSAT, satellite radio, and many other amateur radio activities. So it's fun to talk with him. Because of that involvement, he has chosen to downlink all this data on the 70 centimeter ham band. We get very good range, and it's nice. We don't even have to do RDF. If everything works nicely, we just open up, literally, look at the cell phone, it tells us where the rocket is. In fact, it's in my pocket on most launches and talking to me, telling me like, oh, speed, altitude, range. It's using a synthetic voice to just talk to us all and tell us what the rocket's doing so we can watch it while listening about what's going on. So what's neat, if you look at the sensors, they have one accelerometer straight down the axis of the rocket that is good to 105 Gs. So that tells you about some of the places these engineers and these hobbyists are going. Extreme thrust, extreme lightweight rockets, multi-stage rockets. They put that in there specifically for motor research because some of these individuals make their own motors. We don't let students do that because I really don't want them blowing themselves up by accident. It'd be too much paperwork. So, but, and of course we care about the students. I'm kidding about that, of course. But the 3-axis systems are really what we read most of our data off of. It's rare that we go above 16 Gs. It's rare, hopefully we're not going above 2,000 degrees a second on rotation. But this is really the data set you would expect to have on landing. You can reconstruct the entire flight. In fact, we don't have to do that. The software automatically does that. We can automatically export to Google Maps. And there's a lot of extra capability here to be had, but really, this is what I'm here to talk about today. That we receive most of our data live downlinked on the 70 centimeter band. As a backup, we have a big red bead. Do you have it up here with you? Oh yeah. We generally scientifically duct tape this to one of our parachute cords. And this is basically just your classic RDF beacon. It's just, it'll, every minute, or you can program it, how often you want, it'll beep out in Morse code your call sign, and then it just beeps about every second, every 2 seconds, depending on what power level you want. I think right now it's set to 16 milliwatts. That's plenty of power to go where you want. In fact, it's problematic that once we get within about 100 yards of this without an attenuator, it just sounds equal loudness in every direction. So hopefully you brought your attenuators with your direction finding gear today. But that's our backup system. Works really nice. They're fairly cheap and provide some redundancy for our search operations. So on the occasion that perhaps GPS lock was lost or data link to the rocket was lost, we don't have that nice dot on our phone saying your rocket is exactly here. We have a secondary method of finding our payload and recovering all that information. As far as antennas go, this is what we started with, and we were quick to replace it for various reasons. First of all, we had to just give it to Jared and have him try to follow the rocket. We didn't get to watch the fun. He had to sit there and point the antenna at it. Jared or some of our other students, which we belovedly call meat servos. They can just... The SDR, it's actually a little tiny SDR. It's the size of like a little USB thumb drive, but the way it's mounted with the connector straight onto the PC board basically just screams, this is going to break at any second, especially working out in the field where sometimes things get tossed into a truck. We could have pulled the cord out and it's just in pieces at any moment. And the computer we're using is also not ideal. How many of you ever tried to use a laptop in direct sunlight outdoors? Yeah. The screen's pretty tough to see, right? And so a lot of these things were not optimal, so we modified the system pretty quickly, and this is really neat. This is very commonly used amongst the Rocketeers up there in Argonia, the Cloudbusters group. It's called the TeleBT. So this is also, you recognize the color scheme of the antenna, right? Mm-hmm. What brand is it? It's Aero. Aero. Right, so this Aero makes satellite antennas, one of which we still do use for the DF if we have to go down to that. This is a nice little handheld, 70 centimeter, 3-element. Yeah, not as directional, but okay. We're not shooting rockets miles and miles away. We have direct line of sight to them way up in the sky. You don't need sporadic E to get to contact with these. But what's neat is this is almost its own little repeater. This little box has a little SDR in it, interprets a signal coming down from the rocket, and then rebroadcasts it through Bluetooth to my cell phone, or to anyone's cell phone in the region. Or actually, this would be directly linked to mine, digital link, but others with the same type of Bluetooth system could receive our data, track the rocket, so our customer group, who's present at most launches, can also receive the data live, can also see where it's going. And the occasion that the system was lost, and the occasion the system's parachute didn't function as needed, we at least get the data before the controller boards return to dust on impact. So it's neat that it's coming down, it's all handled inside of that little tiny blue box, and then rebroadcast to my phone and save that. If we had to go to the RDF side, we would use the Aero satellite antenna. I got into ham radio specifically to get the certification to allow my call sign to be put on this Telemega, our telemetry system. Because of the powered outputs and the frequency it operates, we had to have ham radio certification. So that's what brought me here to take the technician exam. Then I went crazy, got into satellite radio and started doing AMSAT contacts, AO 91, 92. And then I learned about these Aero antennas, and of course we needed one for RDF. But it is a suitable backup, it's wonderful. So 2 meter and 70 centimeter, we're going to actually probably found this while making this presentation, a nice little NFJ attenuator. Because like I said, I go through one test I've done of our backup system. I got within about 100 yards of the beacon and then could not tell a difference in signal strength no matter how it turned. So clicking on some nice attenuation would be a wonderful option to continue to track it. And this is what our radio data link actually uses. So what's going on with the Telemega, it uses FSK, frequency shift keying, to send the ones and zeros down of our data system. It's a half duplex system, single frequency, so only the receiver or the rocket can talk at once on that one frequency. Whenever it's on the pad, it's in kind of a very low power, low data rate mode. It's hanging out, it tells us the status of systems, it tells us if we have the arming switches in, if our pyrotechnics are live, it tells us that things are ready or not. And then it's always waiting and checking to detect that acceleration event of launch. And once it does, it goes into what's called fast mode, where instead of pausing and waiting and being nice and cordial on the data link, the rocket just takes over and starts blasting data out as fast as it can on a send. It doesn't care about taking commands at that point, it's just sending data down to anybody who wants to listen on the ground with FSK. Specifically, it's GFSK, and I'll get into some of the differences there, which they're minor, but hey, it's a radio talk, so that could be interesting to you. We're achieving a whole total of 19.2 kilobits a second. Not great, not bad. 3.6 eruption, if you've watched Chernobyl, it's a great show. Only 10 to 40 milliwatts of power. Not a whole lot of power, but still gets you up to 100,000 plus feet with a simple, horrible little antenna. I say horrible only because it doesn't have much gain, it's omnidirectional, but it's plenty good for what we do. We've not launched Link yet.
Well, if your tower is at 100,000 feet.
Yes. Yeah, we've got some good propagation. But we do have to assign a radio call sign to this link, and it can pull off APRS, though really thankfully with the software on the phones, the software through the TeleBT, the software through the data link itself, we've never had to rely on an APRS packet, never had to rely on RDF yet. Those options do exist if we needed it. This is what the signal would look like if you actually fired up an SDR and listened to FSK, GFSK specifically. And what that's doing is turning your ones and zeros of the data stream at 19.2 kilobits a second into basically FM modulated frequency shifting. So it's 2 tones. If you do that exceptionally fast, you start getting patterns that look like this. If you just shot ones and zeros through RF, we get the pattern you show on the left. That's called on-off keying. I should pause to say this is a study experiment conducted by Milan Karakas. Found this online. It's actually from Croatia, so thanks to him for conducting the study, posting the data online. Credit goes to 9A4GE for this data. But what's neat is I've seen this pattern on HF all the time. And it's called a switching mode power supply I have plugged in my wall. It's just turning on and off power to some device and just smashing HF bands. That's why I can't really do much HF at home. So this is bad. Don't do that. I mean, it works, you'll send data, but look how much energy you're spewing outside of the band of interest. If you go to frequency shift keying, where you're not just turning a signal on and off, you're not creating those harsh square wave edges, you're focusing much more of the energy now into a narrower passband, getting much fewer out of band harmonics, and it's an improvement. But the reason that this Telemega and the reason that Altus Metro went to GFSK, what the G means is Gaussian. It smooths the harsh edges of the transition of the signal. So instead of going from a 1 to a 0, from a +1 shift on frequency to a -1 shift on the frequency, it will slowly slew back, well, not slowly in RF terms, right? So extremely fast, but it slews between them, essentially rounding off the corners of the actual waveform you might see, reducing the number of harmonics that the Fourier transform would produce, and all that means is there's less stuff out of there. all of the energy you put towards the signal stays inside the narrow band of transmission, and you stop smashing the entire HF band. You stop getting a lot of harmonics visible outside of the band, and now you can squeeze more signals more closely to one another, sending more power into the data you care about. And it's just better, it's cleaner. So it's an interesting insight that thanks to doing this talk, we could deeper into, and I thought you might find interesting as well. So GFSK, that's why it exists, those are the advantages, and now you can squeeze a lot more signals into the same bandwidth. So shifting back to what the students do. This is the senior capstone competition last year. Just pretty neat. Their competition's cool in that it's basically 8,000 foot altitude rocket golf. The challenge was to take a golf ball to 8,000 feet and return it back to the cup, essentially. They put a flag out in the field and said, you have to pass 8,000 feet, and you have to get as close as you can to the cup. So again, regionally in Argonia, Kansas, using the same type of systems. In fact, this board, you can recognize the same type of hardware, the same type of deployment devices, telemetry, this is the same telemega. Just a smaller package. Is exactly what they flew in this rocket system. So they go through and we teach some basic link margin calculations. Radio frequency activities all throughout aerospace. Every aerospace vehicle in the modern world has one, oftentimes many more data links to and from it, right? Satellites, jets, commercial airplanes, RC airplanes, $10 quadcopters have radio links going to them. And so we teach that. We teach the basics, how to estimate a link margin, and this is what they've done for their FPV, first person vision system. What's cool is they put a camera on the front of their rocket. This little top part was to detach and glide back down and bring the golf ball back down to a star. It didn't exactly work as expected, but there was a good learning process involved, right? So they did the link margin both at long range, meaning high altitude, when the rocket's 10,000, 13,000 feet up in the air. They calculated they actually have 11.4 dB of link margin, should have a positive signal lock given the capability of the receiver, given the transmission gain and transmission power. They're actually able to go through and we teach about 2 or 3 lectures on the topic, and they're able to execute the calculations. Interestingly enough, their FPV goggles have antenna diversity for reception. So we were able to mount both a directional antenna, which one student, again, was just guiding towards the system, roughly, as a directional circularly polarized Yagi. Well, it's actually helical, I have to take that back, it's a helical antenna. And then for the final approach, FPV, we shifted to a broader pattern patch antenna, again, circularly polarized. So that way they don't have to be as exact, and you wouldn't have to track the rocket exactly as it's in the near field. The link margin wasn't as big of a deal. So you see, even with the worst antenna, you have a better link margin when it's close in anyway. That kind of makes sense, right? It's a closer broadcast, closer reception. And this allowed basically the pilot through the goggles to fly the airplane like they were sitting into it right down to the target. It was a really neat concept, and hopefully we'll get to see that succeed here in next year and the year after. So it's really neat to work with these students. It's really neat to see the rocket systems. And I think we have one other video we can show from the November launch to close things out as you guys think of any questions you might want to ask.
What we use from Norman. It's flying a rocket called Baby's Rocket. This is one of their test rockets, flying on an Aerojet N2000 motor. And here we go in 5, 4, 3, 2, 1.
Second pyrotechnic charge deploys with the main parachute coming out, so it takes a few seconds to unfurl. At that point, it should be down around 20 to 30 feet per second. We let it just touch the ground. The customer wanted 2 launches that day. We're able to get them both off, one in the morning, one in the afternoon. So not simultaneous, but at the same time. Same thing.
I think he hears all the different seconds of that.
Images from our lab and our production. See, this is Professor standing by while the student does all the work. that gives you a sense of scale for the rocket. You saw Kaylee lowering these. These are large devices. Actually stuck into a riverbed that way. We found it that way on the ground. All in one piece. All right, so that's what we have.
Very good. We use for source of propulsion.
Source of propulsion, we buy the motors. Again, the most dangerous time in the creation of a motor is whenever the propellant is liquid and you have to mix it. That can be very easily ignited at that point. Unfortunately, there have been lots of accidents of amateurs mixing their own propellant, so kind of as a blanket rule, we don't. We spend the money to buy those so the students are safe. It's called ammonium perchlorate composite propellant, APCP. And it's nice because it's through lots of effort of TRA and amateur rocketeers, you can actually send it through the mail. You just buy them and they arrive in a box. There's hazmat shipping involved, but it's before you put it inside the pressure vessel that forms the rocket motor, it won't detonate, it deflagrates. So even if it caught on fire, it just burns really fast. It doesn't pop. Once you do put it in that metallic casing, of course, the danger level goes up, and we wait till usually the day before the launch to actually mount and put the motors into one element to allow, we have to do it at least 24 hours to allow the glue and adhesives to dry, but that's why we wait. We ship all of our igniters and propellants separate, but it's, to answer your question directly, APCP, very common propellant made principally by Aerotech Rocketry and Cicero.
The C4s.
Yes?
Do you design any multi-stage rockets?
We've been asked to go that route. So the customer likes to go bigger and better pretty fast. The challenge with that is students shift out every year, right? So we're constantly bringing in students, we're constantly graduating students, hopefully, ideally. And so we have to keep that level of expertise going.
One follow-up.
Of course.
Can the public come out and watch these launches?
Absolutely. In fact, that's a perfect question because the Cloudbusters are hosting what's called LDRS, Large Dangerous Rocket Systems. If that sounds cool to you, they're hosting that, I think, later this year. Do you know when they're doing it? And you search for Cloudbusters with a K. But anyways, later in the year, that's the show to go watch because all the rocket clubs around the country fight for rights to host that. It happens to be in kind of our backyard up in South Kansas, so it's 2 hours-ish away from Norman. It's what you want to go see. That rocket, the fin, is probably as tall as I am. These guys go crazy with what they do. It's neat. It's fun. Sir?
So, I thought this was just goofing around for educational purposes. But you're talking, well, yeah, I mean, it's funny, but,
Right.
but you're talking about commercial customers. What kind of payload are people paying you to launch? Because, I mean, I get it if you're going into orbit, that's,
Right.
I understand that, but you're doing near space if you go to 100K.
Right.
What kind of, I am shocked to learn that you have commercial customers. I'm excited and
Yeah.
happy, but surprised.
I will say definitively that we would not be at the level of activity we are without having corporate sponsorship in this enterprise. But the customers asked to remain rather unidentified in their payloads. They sometimes don't even tell us what's in them other than it's safe.
Oh, it's a government contract.
So,
I kind of figured that was going to be the answer.
what kind of things? The design specifications we're given to meet are generally acceleration specifications, altitude ranges, impulse ranges, weight. So they tell us the performance they want from the rocket, what we need to fit, and that's about
What would
right.
they gain by this? Acceleration or altitude?
I've probably said about what I can.
But I mean, but being in space, being up in that area is what they gain. Putting them in that area is what they gain.
They certainly have been coming back and they want us to do a lot more of it. So we've been meeting their goals.
So their payloads come back down, they don't.
Well, they'll come back down one way or another. But yeah, thankfully, the wonderful thing about the customer, I'll say this, much to their credit, they know they're working in an academic environment. They know they're working with students. There was one circumstance where we had a main parachute that, we had it stored in a bag initially, where on deployment, the bag would come off the parachute, protects it from tangles, protects it from the pyrotechnic device firing. But unfortunately, the tether on the bag ripped off, so we had this nice, large parachute that rode all the way back down inside of its Kevlar bag. Obviously, their payload suffered on that impact. The drogue chute kept it slow. It didn't come in ballistic. It was still fast enough to cause damage to a rocket, damage to their stuff, and they're like, hey, happens. They understand the academic, they understand the risk involved. Man.
If you don't know what's in there, how do you know when to say it's a bad customer? It's a bad project, it's something that's gonna be harmful.
Well, in this circumstance, I'm speaking publicly. Whenever we have interfaces with the customer,
You know what's in there.
we're aware.
You're,
Right.
you're
I
not
can't
setting
comment
off an
here on what's
EMP
there.
or anything like that.
Correct. I know that it's safe. So in fact, they sometimes leave us with the payload and it has holes. We can look inside. We know what's there. They've asked that we don't comment too much on who or what or why.
What kind of size on this?
Size, so the size range we can comment on. So the rockets are requested either usually 6-inch, 8-inch diameter. They could, of course, now want to go to 12-inch and larger and taller and bigger impulse. And pretty soon it's going to be SpaceX in North Oklahoma. But
Put Jared in the next one?
just put them in there, freshman guidance system. No. That's kind of what the FPV system is for, right? It's human control, but in a safe way. But
You've got to upgrade to general first.
we would be able to launch payloads anywhere from small to probably 20 to 50 pounds. These rockets have extreme capability. For example, the average motor thrust, they rate them in newtons, of course, some foreign unit, translates to about anywhere from 700 pounds of thrust to 1,700 pounds of thrust. In fact, one of our keystone launches, I would say, would be the launch of the M6000. Yeah. The M6000, so it's M-level impulse, 6,000 newtons average thrust is what the numbers mean. So whatever 6,000 newtons is in pounds, I don't know off the top of my head. Suffice to say, I think it's around 1,700 pounds for us. Those motors have a reputation for CATO, just blowing up rockets on the path, structural failures. They have a reputation for breaking people's nice rocket ships. So much so that the owner of Aerotech, the company that made our motor, came tripping and stumbling across the pasture when he heard that we were about to launch. They announced it over their PA system. And he was excited. He's like, yeah, it didn't blow up. And we were very happy too. But it's one of the highest pressure, highest thrust motors, and thankfully our rocket handled it just fine. So we went, basically handled the entire end impulse in like 1.5 seconds of burn.
0 to the speed of sound.
Yeah, so it's supersonic in 1.5 seconds. It's, some of these accelerations are insane. They will beat a top fuel dragster straight up.
How direct are the trajectories coming down?
Surprisingly close, even when it's windy. What's interesting with rockets, if, say you do have a windy day, because it's never windy in Kansas, say the wind is coming from the south. When it's in rocket mode and it's stable, it will actually fly into the wind. It weathercocks into the wind just like the weather vane on top of your house or on top of a barn or something. Whenever it's under parachute, it'll actually drift with the wind. So, interesting enough, if you set the deployment altitude of the main parachute right-ish or close-ish, it's not uncommon that we're worried about the rockets under main parachute just float right back to our launch site. So under power and under coast, it goes away from you, pops the chutes, and then drifts back down-ish towards you. Most of them land in a 1 mile, 2 mile radius.
Well, because I was thinking of Amazon coming into Oklahoma. I mean,
Rocket
maybe
delivery
every
packages.
other man.
That's one thing, that we are looking for places to launch in Oklahoma, so away from metropolitan areas, away from airspace, so if you guys have
I was
insight
gonna say,
to...
what about the spaceport?
Yeah.
I've inquired about that. Unfortunately, they're pretty close to Burns Flat, the town, so we wouldn't want to risk putting a rocket right back into someone's backyard. So that's where I went first, was a spaceport airspace, but for various reasons that didn't quite work out. Any further questions?